So, our last speaker for today, we're very happy to have Graeme Smith from CU Boulder Physics and GILA, which I never know what it stands for. Joint something lab.
No, they changed it. It stands for nothing.
Oh, it actually stands for nothing. Yeah. I see. Okay, very good. Yes, so just GILA. Yeah, so he's going to be giving us 2 lectures on the role of tensors in quantum things.
Okay.
So, take it away.
Thanks, Josh, for having me, and thank you for showing up. I kind of split the 2 talks into 2 talks, and the first one is going to be kind of like a real quick introduction to quantum computing and quantum information. So I'll talk about sort of what qubits are and what the rules of quantum computing are, and then I'll show you an example quantum algorithm and point out or mention that quantum algorithms can actually outperform classical algorithms in some settings. And that has a lot to do with entanglement that develops in the quantum computer as you run your algorithm. But in order to really clarify that, we have to talk a little bit about what is entanglement and how do you measure it, that sort of thing. Then next talk will kind of be like, you know, three little stories about how tensors come up in quantum computing. Okay, so the only tensors in this talk will be vectors. That's a little joke for you. Okay, so can I just ask briefly, who took a quantum mechanics class once? Okay, and then who didn't? Okay, very good. Quantum computing actually requires very little quantum mechanics in it. Yes, we got some superposition jokes already. Okay, so the first thing I want to do is tell you just, you know, what are qubits and sort of what are the basic building blocks of quantum computation. So first thing I want to talk about actually is 1 qubit. So that's just a 2-level quantum system. It has a state that you can describe as a unit vector, complex unit vector. Okay, and I'm kind of writing it in this annoying to mathematicians but useful to physicists way of kets and bras and stuff. Okay, this just means it's normalized. I have some basis. So I'm going to call my basis vectors. There will be orthogonal 0 and 1, just alpha, and so an arbitrary state will be alpha 0 plus beta 1. So that's like the full state of my 1 qubit quantum computer. I probably want to have some dynamics. State. And those are very, very simple. Actually, you can just multiply your state vector by a unitary matrix. Right, so you can start with some psi naught, and it's a unit vector just rotated in some direction, and you get some output. Okay, and U should be unitary. And then one more thing that I need if I want to really talk about a quantum computer is some measurements. And the simplest thing you can do is you just get to measure in the 0-1 basis. And what does that mean? You get measure in 0-1 basis. And what happens is you get an outcome that's either 0 or 1, and the probability of getting a 0 is just this, and the probability of getting a 1 is that. And actually, after you do the measurement, it sort of resets the state of your qubit. We say it collapses to 0 in this case, or 1 in that case. Okay. And I'm going to draw a picture of what that looks like. I usually draw qubits as a line, so like you might have some state here, and then I'll draw a box with a little dial on it. Right? So the dial sort of goes either to the left, the right, or the left, and that's sort of my one bit of information I can extract. Okay, so this is 1 qubit. It's a little bit dull in terms of computation. So we should add a second qubit. Okay? And then it gets a little more interesting. Is there any question here yet?
0 and 1 are orthogonal.
Yes, they're orthogonal. Yeah. I just want to make sure I do this right. Yep. Okay, so sorry.
You can start going. And it'll get there.
Okay. So now let's look at 2 qubits. So in that case, well, the state of my computer is just going to be a unit vector in C2 cross C2. It better be normalized. And I now have a basis that I'll write like this: 0, 0, 0, 1, 1, 0, and 1, 1. So it's just a tensor product of the 2 bases that you would have gotten from using 0 and 1 here. And the dynamics, okay, so here's the state. The dynamics are a little more interesting. In principle, I can just do any unitary again, right? I can have some initial state psi naught, and then rotate it with the unitary, and I get some output state. But actually, they're sort of like, if you were doing an experiment or you're actually trying to implement this, there are some like easy unitaries and hard unitaries to do. So the easiest ones are like 1 qubit unitaries. So U1 tensor identity on the second qubit, or identity on the first qubit tensor, some arbitrary unitary on the second qubit. And maybe I can call it easy-ish, is a control knot. So I'm going to express what the control knot does in terms of that basis. It just leaves this first qubit alone. This is the target qubit, the control qubit and the target qubit. It just adds x into it, mod 2. Okay? So this is called a control knot. If you want the unitary, it's this. Okay? Where I've ordered these guys sort of in this order. So 0, 0, 0, 1, 1, 0, 1, 1. Same down there. Okay, these are the dynamics. I also need some measurements. And again, when you're talking about quantum computation, usually it's just enough to think about, well, I get to measure in this basis, they're orthogonal, and the probability that I get like a 0, 0 is just the inner product of 0, 0 with my state squared. And sometimes we call this the classical basis or the computational basis. And now something interesting happens because these 2 gates together, the easy and easy-ish ones, they are universal. And by which I mean, if I take any unitary in, let's see, any 4x4 unitary, U, I can always, given some epsilon, find some sequence of 1 qubit and C0 gates. So that, well, it's not exactly equal, but up to any epsilon I choose, I can always get as close as I like to the unitary the target unitary I have. Okay, and now you can see we're sort of getting into a situation where there's some notion of how hard a computation is, because some unitaries are going to be really easy to approximate with a small number of C0s and single qubit gates, and other unitaries are going to require lots of them. Okay, good. So if you were to guess what the next board is going to be about. 1, 2, and then many, right? So we're going to have many qubits. Let me just erase this. Oh, okay.
You erase, I'll switch them.
Oh, thanks. And actually, you likely fill this in yourself. If I say I have n qubits, well, my state is just going to be some really big unit vector. My dynamics, in principle, are going to be all unitaries, but actually, it's going to be useful to just talk about all the 1 qubit unitaries. And a bunch of C0s, so C0s between any pairs. Okay, any pairs. And our measurements. Well, now I'm going to have a basis that like is a bunch of n-bit strings. And my measurements are just going to be in that basis, and the probability of getting a given outcome, a given string, is just going to be equal to the norm squared, sorry, the amplitude squared of the state in that basis vector. Yeah?
Why do all the C naughts have to all be in pairs? Can you do things with triples?
Can you repeat that?
Yes. Why do the C0s only have to be in pairs? Can you do things with pairs and triples? Right? They don't have to be, but this is good enough because if I give you just these, then you can actually generate, they're universal, so you can generate any unitary you like, so you could generate a unitary on triples if you like. And then like if you want to implement it, actually, usually you just want to make pairs talk to each other because it's easier. Okay, so now we have a real computational model here, right? We have some qubits. We can do some single qubit gates. We can do pairs of 2 qubit gates like this. And we can start to ask, well, what kinds of questions can you answer by using a machine that can do this kind of stuff? Okay, and then at the end, we're going to do some measurement like this. Okay, and again, I said this is a universal gate set. But actually, we're going to be interested in stuff that you can do by using like a polynomial in n number of gates in your circuit. And the number of unitaries you can actually get to, you know, these unitaries now are going to be on 2 to the n by 2 to the n dimensional, or going to be 2 to the n by 2 to the n matrices. So actually, the number of unitaries you can get close to for a polynomial sized circuit actually becomes very small compared to the total number of unitaries. Okay, so then the question kind of becomes, well, what can you do with this model? Okay, so here's one thing you can do, classical computation. And the way to see that you can do classical computation using this is, you can use sort of like 6 C0s in a way that I won't show you, but I could show you, to make something called a Toffoli gate. That's a controlled knot. What does it do? It has 2 control qubits and 1 target qubit, and it just leaves the controls alone and adds the product of those. So it basically flips the bit exactly when you got a 1 here and a 1 here. Let's see, Toffoli. And this gate alone is universal for classical computation. So anything you can do on a classical computer, you could also do with a quantum computer like this. So that's kind of interesting, but not really. What you really would like to know is what more can I do with a quantum computer that I can't do with a classical computer? Something more. So what I'd like to do now is show you a specific example of an algorithm that can outperform all classical algorithms for the same task. It's sort of like one of the earliest quantum algorithms. It's called the Deutsch-Jozsa algorithm. Okay, and it's going to involve a specific gate that is kind of like, well, it's kind of like a very non-classical gate called the Hadamard. It's a single qubit gate. So you see it's a unitary, and it just maps a zero vector, or sorry, a zero state to a plus state, and a 1 state, we call this plus, to a minus state. Okay, so some mention of superposition. This is something that makes like an equal superposition of the two sort of the two logical states, the computational basis states. So it's sort of like really quantum. Deutsch-Jozsa is going to use this Hadamard to solve the following problem. I promise that some function I have on n bits to a single bit is one of 2 things. So it's okay. It's either a constant or balanced. Balanced meaning like on half of the inputs it's 0 and the other half of the inputs it's 1. And your job is to determine which is the case. Okay, so how many function calls do you need? N over 2 plus 1. Classically, 2 to the n over 2 plus 1. Right? And then that's if you want to like know deterministically, right? You can also do a randomized algorithm. Then you can sort of get within a probability of error epsilon. You can do it with sort of log base 2 1 over epsilon queries. Okay. So then, what about the quantum answer? 1? No. Just a single query. Wow. No. Yes, it's true. You can do it with exactly one query. So this is kind of a cooked up problem. but it is an interesting one. First, because in the time allowed, we can actually see how this works. Second, because there's a straight line from this to another problem, which is a little more complicated, Simon's problem, to Shor's algorithm, right? So Shor's algorithm is a way of using a quantum computer to factor numbers. Shor was inspired by Simon's algorithm, which was in turn an attempt to, or a successful attempt to address the fact that we don't really like that the gap between 1 and log 1 over epsilon isn't like big. So Simon's algorithm gets an exponential gap even for randomized algorithms. But the cost of those is that they're more complicated. But, okay, so let's look at how this actually works. Okay, first I have to tell you how we're going to query the function. Here's how, well, it's got to be in the form of some unitary because the dynamics in a quantum computer are always unitary, so if I'm going to be querying the function on my quantum computer, I better have a unitary. So it's going to take x, the input string, and some y as inputs, and it's going to leave x and just put the function value into the last bit. So there are n qubits here and 1 qubit there. And here's how the algorithm works. I take a bunch of zeros and a 1. I apply a bunch of Hadamards. I feed them, okay, I'll call this use of f. I feed them into my, my unitary. I apply a bunch of Hadamards again. You don't have to worry about that, okay. And then I measure these. And I can measure that if I like. Actually, it's going to turn out that I don't need to even look at the output of the, at the output bit of the oracle. Okay, so I claim that by looking at the measurement outcomes here, I'm going to be able to figure out whether my function was constant or balanced. And in particular, I'm going to be able to see, I'm going to be able to tell by looking at the probability of getting all zeros up. Okay, so let me just write down what the state is at various steps in the computation. Okay. Well, at the first stage, let me give you these some names. Psi 0, psi 1, psi 2, psi 3. Okay, so psi 0 is just a bunch of zeros tensor 1. Psi 1 is 1 over 2 to the square root of 2 to the n plus 1 times sum over all x's x tensor 0 minus 1. So why is that? The Hadamard just took each 0 and turned it into a plus, and then it just turned all of these registers into a tensor product of a bunch of pluses. And that just gives you something with, everybody has the same amplitude in front of them with no minus signs, except for the 1 qubit that had a 1 on it that turned into a minus. Okay? So that's pretty simple, and you can see what we're going to do is we're going to be querying this oracle on a uniform superposition of all the possible inputs of the function. That's kind of how it's going to work, that just a single query can give us the answer, because we query it on sort of all of the different inputs at the same time. Okay, that's psi 1. Now we have to figure out what happens when we apply the oracle. We're going to get psi 2. And it's not so bad. It just, well, it leaves all of those alone, except it just puts the value of the function down into the last qubit. Right, and now the value of the function is either 0 or 1. So no matter what happens, this is going to be, well, if the function is 0, it'll be 0 minus 1. And if the function is 1, it'll be 1 minus 0. So it's actually going to be proportional to minus, the minus state. There's just going to be like an extra phase in there. So this is sort of equal to 2 to the n plus 1, sum over x, minus 1 to the f of x, x, 0 minus 1. Okay, and you can see now why we're allowed to forget this, because this state no longer, the state of this qubit no longer depends on, or has any dependence on x, or actually anything about the function, right? All of the information about the function is now in these top qubits. So now when you apply the Hadamard one more time to all of these qubits at the top, what happens? Let's see. Well, here's what it does. Well, you get another factor of 1 over 2 to the n. Now it's going to be a sum over x minus 1 to the f of x times the sum over y, again, n-bit vectors, minus 1 to the x dot y, y, and then you get the minus state here. And now if I measure this in the computational basis and say, what's the probability of having measured all zeros? It's going to be this thing. The amplitude squared of 1 over 2 to the n, sum over x, minus 1, the f of x. Well, y is 0, because I'm trying to figure out the probability of measuring 0. So it's this big sum, amplitude squared. And now that's great, because if f is constant, all of these things are the same. They're all either minus 1 or 1. And then that gives me the amplitude squared of either minus 1 or 1. So I get just a 1 if f is constant. And if half of them are 0 and half are 1, I get like half of the terms in the sum are plus 1 and half the terms are minus 1. So I get 0. So I get 0 if f is balanced. Okay, so you see now with one query, I managed to figure out whether I've got a constant or balanced function. So that's, I guess, a quick example of one quantum algorithm that does a pretty good job, well, does an okay job outperforming classical algorithms. Yeah? If it wasn't for this probabilistic strategy, it would be a really good job. So there are many improvements that make us sort of increasingly convinced that actually you can do, you can do better. There are problems that quantum computers can solve faster than classical, even exponentially faster. So for instance, Simon's problem. It's a lot like the Deutsch-Jozsa problem, except now you have a function from n-bit strings to n-bit strings. And I promise you that for some s, if I evaluate the function on x plus s, it's always equal to the function on x. And then your task is find s. And then in that case, we actually get a classical lower bound to the number of queries we need, even for probabilistic algorithms of 2 to the n over 2. And we can solve the problem quantumly with order n queries. Okay, so it's a genuine separation between what the quantum and classical computer can do. Of course, there's also Shor's algorithm. And this can factor, oh, somebody said something. You, in the back.
Now, what do you have written? It equals 1 if f is what?
Constant.
Oh, okay.
Yeah, and 0 if it's balanced. So it can factor numbers in sort of order log n cubed time, whereas classically it looks like it's something more like exponential in the third root of n. So you can sort of exponential separation there. Also, there's another sort of flavor of algorithm that you can get where you can find a marked string in time square root of 2 to the n. Like if you have an n-bit string you're looking for, you can find a marked string in time square root of 2 to the n instead of classically, which takes time 2 to the n. Now, I don't want to get too much into my curmudgeon hat, but you may have heard of all sorts of other fancy quantum algorithms. You may have heard that quantum computers are going to speed up machine learning and are going to give you exponential speedups for optimization problems. And generally, you shouldn't really buy that. Those are more aspirations than results. Yeah.
So, question. So Grover's classical, is that an absolute lower bound?
Yeah. Oh, sorry. Is Grover's classical is the lower bound for, well, is this a lower bound for Grover's problem? Yes. So basically, in that case, you have an oracle, and there's a single string that it evaluates to 1 on, and it's 0 on everything else. So the lower bound, I mean, think of it this way. For deterministically, you basically got to check everything, and you're not going to get lucky, probably, so like it's still not going to help. Yeah?
So, other than factoring, the other problems in here aren't necessarily even an NP, so there's still, and even factoring might not be complete.
Uh-huh.
So, none of this gives you a separation between problems that are an NP and BQP, right?
No.
Like, in general, there shouldn't be any evidence for that yet.
I can draw one of these pictures, okay? So here's BPP, and that's an NP, and then even we kind of think like BQP is like this. Yeah, so there's no evidence at all that BQP contains NP. There are lots of problems that we kind of think quantum computers are good at doing, but you can't easily check. That's actually becoming a really big problem now because people are building quantum computers that are too big to simulate classically, and the question of how you check that they've sort of actually correctly answered the question, well, how you check whether they've answered the question correctly is an issue. And, well, I guess, there is one more problem that I should have mentioned, that we do believe quantum computers are good for solving, and that's simulating quantum systems, specifically the dynamics of quantum systems that have lots of entanglement in them. That seems to be a hard thing to do classically, and and it's also something that quantum computers seem to be able to do a reasonable job at. So that's like, I guess, quantum simulation is another kind of possible place where we could apply a quantum computer. Okay, so I said entanglement. Now, this, I guess, up to now, I guess I just wanted to argue that, well, there are things that quantum computers can do better than classical computers. The generic answer for why is that quantum computers have entanglement, and classical computers don't have entanglement, so maybe, well, that explains why you can do more with a quantum computer. So I want to speak a little bit about what do we mean by entanglement, why do we think it's hard to simulate classically, and maybe that will be sort of for next lecture. This time I just want to kind of define what entanglement is and say something about the ways that we try to quantify it. Okay. So in order to do this, I kind of have to introduce just a little bit more I forgot the word I was trying to use. Stuff, okay? Just a little formalism, that's what I wanted to say. A little more formalism. So we talked about how the state of my quantum computer I can describe as a unit vector, and the dynamics are just unitaries, and the measurements I can think of, especially when I'm doing computation, as just projective, or as just projecting into an orthogonal basis. We're going to have to sort of make a slight jump beyond that if we want to talk about entanglement, and that involves going to, instead of unit vectors, now talking about density matrices. So let's say I have some state on a two-party system. So it's a unit vector in CA tensor CV. There's something called the density matrix of that state, rho AB. And for this state, I just take the projector onto the unit vector. So now instead of, well, now it's just like some square matrix, okay? And we call this the density matrix. And actually, if you just want to describe stuff like experiments that you do on the A system. So, okay, now I have to introduce Alice and Bob. A is for Alice and B is for Bob. These are the people that hold on to the systems A and B. If I just want to describe experiments that Alice is going to do, I actually only need access to rho sub A instead of rho AB. What's that? Well, I do a partial trace of rho AB, where trace over B, what's that? It's just the linear operation that does this. Okay, it just sums over all the indices, the B-like indices in the matrix. Okay, and if I want to describe anything that Alice can learn about her system by doing measurements or applying unitaries, anything she can do to our system, it's enough for me to just know this matrix. So one thing I should say is it has the following properties. First, it's positive. semi-definite. And second, it has trace 1. The same is actually true for row AB, and it inherits these basically from row AB. Okay, so in order to talk about entanglement, first we had to talk about density matrices, and the second thing we have to talk about is a little bit about measurements. So, so if I am restricted to just doing these measurements of a qubit, say in the 0-1 basis, one thing I can do if I have a system with a whole lot of different qubits is sort of bring in a qubit in the 0 state and make the rest of the qubits interact with it very weakly, do a unitary that only barely moves away from the identity, and then measure the qubit I just brought in projectively in the 0-1 basis. And that gives me some partial information about the state without totally collapsing it down to just being a basis vector. If you do that, you can kind of describe a set of measurements that are a priori more general, but can be realized, like I just said, in terms of projective measurements, but are called POVMs, and they're characterized by a set of matrices, E sub k. K indexes the various outcomes of a measurement that you might get. They have to sum like this to the identity. And then if I have a state, I can perform a measurement I can do a measurement associated with these operators that has a probability of getting outcome k that's given by psi e dagger sub k ek psi, and leaves a post-measurement state of just ek psi divided by the square root of the probability of k. And the point is, this is a kind of measurement you can do that lets you get some information that's classical now, without totally collapsing your state. So if these EKs are all kind of close to the identity, they leave the state alone more or less. They don't distort it too much, and at the expense of sort of extracting less information out than a full measurement. Okay. So we've got our density matrices, we've got our POVMs, our sort of generalized measurements. The last thing I need to introduce in order to make precise what we mean by entanglement is a set of operations that I can do on density matrices, kind of that reflects the locality or reflects the separation in the two systems that we're talking about, that we're looking for entanglement between. So let's put it this way. We're interested in LOCC. These are local operations. And classical communication. So the idea you should have in mind is I have some quantum state, psi AB. Maybe actually let's fix a quantum state to think about, psi naught. This is called a maximally entangled pair of qubits. Okay, so I am imagining that Alice has a lab, and the A system of this state sits in Alice's lab. The B system of the state sits in Bob's lab. Alice and Bob can each do arbitrary local unitaries, arbitrary unitaries on their own system, and they can do measurements like this on their own systems, but it's hard for them to do sort of joint operations on the two systems. And this is actually like true if you have two labs, right? Like, it's not that easy to like measure in the do a joint measurement of two different labs in two different parts of a building, say. So let me draw a picture of the kind of protocol that sort of you can do using just these easy steps. Let me make sure I know what time it is. Okay. Well, you can imagine Alice and Bob start off with a qubit each, and let's say they start off in the 0 state, both of them. Well, Alice can do some unitary, and then maybe she'll do some measurement. Again, it'll be described by some measurement operators E sub k. And then having done the measurement, she might phone Bob, and maybe he's done something local too, and then tell him the outcome of her measurement, I1. Bob can do some measurement now that could be conditioned on the outcome of Alice's measurement, and he'll get some outcome. Now, the reason that we had to introduce this notion of a POVM instead of the projective measurements is that this would all be done really fast if we just restricted our attention to projective measurements, because every time you did a measurement here, you just end up in a very simple state again, a tensor product of whatever the measurement outcome was here and whatever he had over here. But by doing these sort of incomplete measurements, you can sort of maintain some quantum, some correlation between the quantum state here and there, even though you did this partial measurement, okay? So you can imagine these guys go back and forth, communicating what their measurement outcomes are and doing further measurements depending on those, and at the end of the day, they'll have some state. Psi AB. Now I'm fine. This is called an LOCC protocol, Local Operations and Classical Communication Protocol. And now I can finally define what I mean by entanglement. Okay, definition. Rho AB is entangled if Alice and Bob just can't make it via LOCC. So if they start off in the 0 state here and they run an LOCC protocol, there's no such protocol that generates their state. If there is such a protocol, we say the state's not entangled, and if there isn't, we say it's entangled. There's an alternative characterization. We say if rho AB can be written as a convex combination of product states, so tensor product states like this. Well, maybe I'll call that sigma. Then we say it's separable. And if you can't, if it's not separable, then it's entangled. Okay, so now we've defined entanglement. Is the key thing that the PIs are positive? Yes, the PIs have to be positive, and these have to be also positive semi-definite, the states. Okay, and now that we've defined what we mean by entangled, I think I told you that this is called the maximally entangled state, and that suggests there's some notion of how entangled is it. The first thing I should say is that these are kind of clumsy definitions, right? So if I give you a density matrix and you want to decide if it's entangled, it's hard. You have to go off and see whether there's such a convex combination. That's not something you can do computationally very easily. For 2 qubits, there are ways to do it. You can do it, but it already gets hard for 3 dimensions by 3 dimensions. hard in the sense that like you can't stare at it, and even, well, how hard is it? If you're going to let the size of your density matrix grow, it's like an NP-hard problem to test whether you have a separable state. So of course, we're very interested in finding ways to take a state and map it to, or say something about what entanglement it's got inside it, right? Like how much entanglement it's got. And again, since LOCC is the set of stuff that can't generate entanglement, it's sort of the set of easy operations. It's very convenient. How entangled? It's a very convenient class of operations to use to try to compare the entanglement in two states. So for instance, if there's some way for me to take some state psi1 between A and B and map it via LOCC protocol to psi2, because the LOCC couldn't create any entanglement, we'll say that psi1 is more entangled than psi2. It's not the case that you can always do this given two states, so it's like a partial ordering, but actually, we actually know how to solve this question of quantifying entangled in the following situation. Asymptotic, bipartite, pure states. What do I mean by asymptotic? I mean, I'm interested in given a, well, okay, let me just write it. 7, okay. Yes, I think it's going to work then. If we let this function, psi of AB, be equal to minus trace of rho A log rho A, then for large N, I can take n copies of psi and map it via LOCC to E, this entropy of AB, times n copies of this maximally entangled state. Furthermore, I can go back. I can take those E times n copies of the maximally entangled state and map it back to n copies of psi. Actually, there are little o(n) corrections here, so I lose a little bit, but for big N, those go away. And in this case of asking about, well, given many copies of my state, how many copies of a maximally entangled state can I get out? And how many maximally entangled states does it take to make the state? I can totally answer that question for bipartite and pure states. And this also tells me like the optimal rate at which I can go from one state to another, because I can always go through maximally entangled states without losing anything. Okay, things get messier. Sort of, if I just keep bipartite and pure states, we still have we can still answer this question about like when can I go from one state to another via LOCC. If I put back in asymptotic and then remove bipartite, so I go to more parties that are doing LOCC where they can do local operations on each of their local labs, then the problem gets really hard. If I go from pure states to mixed states, so density matrices that are not rank 1, Again, I have no clean answer. We have sort of different ways of quantifying the entanglement in different states, depending on what the situation is we're looking at. But no clean sort of expression that says, okay, here's how to quantify the amount of entanglement in that state. So I've taken you through, okay, what are the rules of using qubits? I gave you an example of a quantum algorithm. I said, well, entanglement in the quantum algorithm is kind of the key to it being possible for the quantum algorithm to outperform classical. Then I said, oh, what's the entanglement? What is entanglement anyway? For next lecture on Friday morning, I believe, I want to move to sort of giving you a little tour of how these questions connect up to the theory of tensors. So next time, I want to sort of touch on three topics. The first is matrix product states. And low entanglement quantum computation. What does this mean? It's just going to be a particular kind of state that if your quantum computation always stays in that state, that sort of family of states, there's going to be an efficient classical algorithm for simulating it. I want to talk a little bit about tripartite entanglement. And tensor rank. So it's going to turn out that, remember I said if you remove the bipartite, it becomes unclear what are the rates of interconversion of different quantum states. It's going to turn out for qubit states, or 3 qubit states, if you want to understand the entanglement, it becomes a question about the rank of various tensors. And maybe, if there's time, I'll just draw some pictures about tensor network states. And this sort of connection to ADS-CFT, or toy models of ADS-CFT, which is a duality that exists in high energy physics that seems to be best understood in terms of sort of a generalization of matrix product states to tensor network states. With that, I will stop, and if you have questions, please ask.
Thank you.
Yeah.
So I think the part that I find always confusing is I feel like I could sort of shake dice and roll it and consider some probabilistic events and hope that that would approximate this.
Yeah.
And I'm hoping you're going to tell me that this entanglement by LOCC or something somehow has covered that as, like, whatever is different is hiding inside of this entanglement.
Yes, that's right. That's exactly right. So, for instance, you can... Oh, I'm sorry. I believe...
Why is this not just a probabilistic machine?
Why is this not just a probabilistic machine? There is sort of... So, let me phrase it like this. In terms... Okay, let me show you a game, yeah? Here's a game. There's some referee, and he asks questions to Alice and Bob. X, Y, A, B. Here's Alice. Here's Bob. And make sure you get this right. He's going to send a single bit to Alice and a single bit to Bob, and they're going to each have to answer questions based on, or they're each going to have to send back answers based on what the questions were, and they're going to win if x and y is equal to a plus b. Okay? And they're allowed to talk beforehand, but once the game starts, they're not allowed to talk to each other anymore. And the point is that, well, okay, so if they only share some classical randomness, which is, describing the strategy they're going to use, they can win this with 3/4 probability. However, if they share this state, because they can adaptively, based on the measurement, based on the question, do a different measurement on their part of the state, they can win the game with probability 1 over 2√2, which is like 85% probability. Okay? So what does that mean? It means that the correlations between the questions and the answers that they can generate by measuring halves of maximally entangled states are somehow bigger than the set of correlations they can generate by just having some shared randomness between them. So this is called the CHSH game, and it's a particular example of something called a Bell inequality, and like foundations of physics people would say this shows there's no local hidden variable theory of a maximally entangled pair. So this is kind of like proof that it can't be just a probabilistic machine. Yeah?
So, maybe since it's close to the end of the afternoon, you should bloviate it a little bit.
Yes?
Besides this sort of game, like the CHSH stuff,
Yeah.
I've been confused, even though I sort of used to work in this area. I've been confused about whether any of the algorithms of which we're fond,
Yeah.
Simon, Shores, and so on, are really entanglement heavy, right? And it's always confusing because, as that questioner was alluding to, we often jump from deterministic classical computation
Yeah.
to quantum computation. And of course, classical probabilistic computation can have exponentially large probability vectors and all sorts of correlations.
Yeah.
They just don't have this extra stuff. But when we look at Shor's or Simon's algorithm, is the secret sauce entanglement, or is it simply that we have complex numbers instead of real ones, so that we have both positive and negative interference instead of just adding probabilities up?
Let's see. Well, the interference is a signature of entanglement. How's that? Well, I mean, if you actually, if you try to simulate use DMRG or something to try to simulate implementations of Shor's algorithm, it does have lots of entanglement in it. That's not a proof that it's hard because of the entanglement. It's it's just an indication that. Well, no, it's even worse. It's even better rather. If they don't have lots of entanglement in them, I can simulate them efficiently, and therefore they're not going to outperform classical computers. So I can't. For Shor's algorithm, I believe in that. For Simon's algorithm, there might be some issue that the entanglement would only show up during the intermediate time while you were applying the oracle or something like that.
This is exactly where I get on that.
Okay.
Because if I have a classical probabilistic algorithm,
Yeah.
that is not generally something I can easily simulate with a classical deterministic computer, because again, probability distribution is exponentially big. So, saying that you can do a good job of approximating on a computer with DMRG states,
Yeah.
because there's no entanglement, seems to be incomparable to the claim that you could, because that would not be true of a typical classical probabilistic algorithm either.
Okay, that's right. Okay, so
It's better known.
that is available here. Okay, maybe. I mean, it's okay. So let's put it this way. You're right that the theorems that exist do not say you need zillions of entanglement in order to get a quantum speed up. It just seems to be that way. And, you know, people have these old examples of like using really mixed states to do quantum computation, to do a trace of a really big matrix, right? And that, in some sense, doesn't have, well, it's not clear because we don't have a single way to evaluate how much entanglement there is. It's not clear whether there's lots of entanglement in that or not. I would say that the best ways, or many, okay, yeah, the best ways we know to do this simulation, including probabilistic simulations of quantum computers, do tend to get stuck the more entanglement you get. So. Thanks.